Hi, we're Group 10, and this is our ME-157 design project, the Formula SAE Quick Jack. I'm Matan Bloom.
I'm Joseph Love. I'm Zach Abdallah.
And I'm Tiago Costa.
All right, who's got a motivation and purpose for the project? So we're all members of the university's Formula Student Team, and we spend a lot of time working on 2 different cars. So this car constantly needs to be lifted. Each car weighs almost 450 pounds. Last year's cars weighed 430 pounds, and the other car weighed about 450. So we always lift each car with a minimum of 4 people, 1 person per corner at least. And this happens a lot. So it's a very labor intensive task. And we'd never want anybody to ever drop the car. So we like to try and see if we can avoid doing this. So here's a working principle of our quick jack. So this quick jack needs to easily raise either car off the ground and allow team members to work on the car. So you should be able to raise and lower the car with manual cranking it manually, or by using an electronic tool to turn the crank. And it has to be low enough to place underneath the body of the car with relative ease. And it has to be stable and hold the car without collapsing. And there needs to be some built-in factor of safety there. And locking would be nice as well.
So here's the house of quality, or QFD, that we use to first come up with our product definition. So we started off with the QFD steps 1 through 3, the who versus what. We have the requirements of our project, as well as potential clients that would use it, such as FSC racing teams, autocross competitors, auto mechanics. And using the fixed sum method, importance values were given to each of these clients and what their priorities would be. For step 4, we did some research on existing models and other models that the team has also used in the past. And we assigned different ratings based on the criteria that we're going to be using for the quick jack that we designed, and doing some background research to see what were some of the strengths and weaknesses of past and current models. Moving on to steps 5 and 6, we compare the what versus how. So here are some more engineering specifications that are more quantitative that we can assign numbers to and use that to later on give goals for our own product that we create ourselves. So here's QFD steps 7 through 8, where we compare the how to each other. And so this is the quantitative engineering targets that we have set for ourselves. We have targets that we would be delighted with, and then also targets that we would not be happy with. So we were able to assign values to these parameters, and we'll be using these as goals for the product that we create. And also for the final step, we compare the relationships between the engineering specifications and see how do they affect each other.
Here we have the design specifications. These are the specifications we came up with at the beginning of our project of things we needed this lift to do. And as you see, we have completed and outpaced everything we needed to do. And this basically just shows that we were able to basically get everything done. The only thing we were not able to do, which we deemed not important, was the weight. For the conceptual design, we had 3 initial designs of how we wanted to move this lift. We ended up going with concept 1, and then using Fuse method, we were able to really nail down what we wanted to do and basically take that concept into a final product. Here we have a recording of how the quick jack is supposed to work, where it gets turned with a crank or with an electric torque driver to be able to go up and down with ease.
Moving on to the kinematic analysis, we first found the angle alpha that the links would be at when the lift was at its fully extended height. we calculated it to be 60.8 degrees, and we use this angle alpha to find the other forces through the links. So we first started with the force on Fy. This force was calculated to be 4,558.9 newtons. And due to symmetry, we were able to relate the forces in the links to each other, and each link was equal to that calculation. We then found the force Fx. This force was found to be 7,959 newtons. Both Fx or Fs and forces through all the links were used in the link FEA that was outlined in our detailed analysis that was submitted previously. We then went through assembly level FEA. All tubes were treated as beams, just so that we could iterate our design quicker and go through our analysis a little bit faster. We constrained the links. We constrained the links at the joints of links 1 through 4. This was to simulate a rigid pin in order to distribute the force through the entire structure. A force of 4,448.22 newtons was applied at the top weldment of the beams. This was to simulate the force of the car, which is roughly 1,000 pounds, to give us a marginal safety factor. We found a factor of safety of 3.3, actual stress of 7.755 newtons per meter squared, and a max displacement of 2.78 millimeters.
Here we have the fatigue failure analysis of our clevis pins that go between each of the 2 links. Here we have them modeled as 18-8 stainless steel clevis pins, and all the assumptions that we have are part of the parts that we would be able to purchase through McMaster, which are used in the calculations in the next slide. In this slide, we have the Martin factors, and these were basically able to help us calculate our endurance limit, which we found to be 197.48 megapascals. Here we have the end of the fatigue failure analysis, where we were able to calculate a factor of safety using D.E. Goodman's failure criteria to find a factor of safety of 1.89.
Next, we have the bearing selection for the wheels. So there were some assumptions that we made based on how often we expected to use the quick jack, as well as the wheels, how long they would be in use. And by knowing the wheel radius as well, we were able to get expected RPM values. And then along with some other assumptions, we were able to do some calculations that allowed us to find the bearing life in revolutions as well as in hours. So using these assumptions, we were able to fill in some of the unknown variables as well as other factors based on the stated assumptions. So A1, A2, alpha, the equivalent force, were all able to be filled in with values based on those assumptions. And we were able to fill in the rest of these variables as well to find our basic load rating, which was found to be about 1.5 kilonewtons. And based on this basic load rating calculation, we were able to go to SKF's catalog, and we found the best matching bearing that most closely matches this basic load rating. And that was a 61-807 single row deep groove ball bearing.
Here's our bill of materials. So listed in the bottom left corner is all of the part numbers that make up our assembly, and an exploded view as well. Here's our bill of materials. So this is, for the most part, our theoretical cost. So we got a bunch of tubes. A lot of these, how this was priced was through a vendor that we typically go to, and it's McMaster Car. Yeah, a lot of off-the-shelf components. The tubes come out to almost $2,000 in materials, but typically we have raw materials such as tubes like 4130, aluminum, like all that stuff is typically sponsored by local companies here in the Bay Area. And here's our references. So the vendor that we priced out all of our materials from is linked here. So you can visit the McMaster-Carr website from here as well.
Thank you.